All right, now you might be wondering, Alan, what are you thinking? The engineer's apprentice, engineers don't have apprentices. They have interns. Although I can draw a few parallels between an apprentice and an intern, because that's how internships originated from, is apprenticeships. So why did I enter an internship? Well, number one, it's required by the university, and no, that is not a nonsense requirement. Because it was what I call the great workforce paradox. You experience to get a job, you need a job to get experience. How do you solve that? Any ideas? Well, the only thing I know is to get an internship. Because they're specifically designed to solve that paradox. As I said, just like a welder or machinist, construction worker, or whatever blue collar worker, or whatever, because the apprenticeship got his feet. With white collar jobs like engineering, you need an internship. So, if it's required, and it solves the paradox, why not put it on your resume? And as this slide, you want to make sure engineering is the right path for you to take, because if it's not the right path for you to take, you're not going to be happy with the job. And crappy job, crappy life. Fun job, fun life. You want to go for something that you enjoy, and engineering is what I enjoy. Is that how they work? I mean, is it like a real job, or is it like a volunteer work? What do you think an internship is? Well, it's like a real job, actually. You have a boss, you clock in and out, you have lots of things to do. You always want to do what you're told, by the way. You can be on campus or off campus. I can be working for a professor like Dr. Bohm or Dr. Valero, or I can work for a huge corporation like Microsoft. I work for a small mom-and-pop company like a machine shop down the street. I can be a mechanical engineer or a CAD worker for them. Be a CNC programmer, you never know. I can work for a professor doing a project. In this case, it was Dr. Shedd. That's what you slide. Now, the difference between an internship and a job, there's really two of them. Well, most of them aren't paid, but there is an increase in trend towards paid internships. But the main focus of an internship is to learn, not earn a living. You're not going to be expected to know everything, and your boss is going to be more like a mentor to you in addition to a boss. He's going to teach you along the way. So he's like, it's like an apprenticeship, as I already said. And you may be thinking it definitely might help you find a job, right? Well, absolutely, as that says. In fact, most people who enter the workforce after college, whether it be engineering or medicine or whatever else, you can very well be hired by the same company who you work for. If you do a really good job and you go above and beyond, they might like you so much that they're just going to hire you fresh out of college. But a lot of people who do well here at Poly will have that happen to them. And that's good, because there are people out there that take years to find jobs after college. And an internship will help you solve that. So you can get on your feet, get out of your parents' house, stop sitting on your butt playing video games, and just do it, like Dr. Valero says. Now let's go to the chicks. What did I do in my internship? Well, I worked as an intern for Professor Shedd, and that internship's been going on for the past summer and all the way into the spring. And the project involved was to test the commercial feasibility of 3D printed polymer heat exchangers. I know that sounds really pretentious, but it's actually a pretty cool technology. What's a heat exchanger? Well, let's just say it's something, it can be anything, that transfers heat from one fluid to another. Although heat is defined as the transfer of energy due to a difference in temperature. Heat transfer is kind of a misnomer, isn't it? But we call it heat transfer just to make it sound easier. So let's get back to this. A car's radiator is a pretty good example. It takes the radiator fluid, cools down the engine, and radiates that out into the air. And yes, air is a fluid. Because a fluid is anything that cannot withstand shear stress. Like, I'm giving the air some shear stress now, right? It can't withstand it, right? My hand's just going right through. It's a fluid. And what the heat sinks we were working on, we're going to be using that as a liquid cooled heat sink for the computer processor. It's like your gaming computer, you have a liquid cooled heat sink. But what if you were to make those out of plastic? Imagine if you can 3D print your own heat sink, save yourself $100 for your computer. And why can't we just use metal, you might be thinking? Like, does metal have a higher thermal conductivity? Can't conduct heat or electricity or whatever else better? Well, number one, you don't really want to conduct electricity with a heat sink. It's on your computer processor. If one of those little pins shorts out, you're pretty much screwed. So metal does have a higher thermal conductivity. You're right about that. That's one of the things that makes metal metal. but polymers are a lot cheaper. And the thing about engineering is you always want to make things cheaper and more reliable. You always want to make it more feasible. So, do you think it's cheaper to get a fancy CNC lathe or mill that costs as much as a Corvette Z06 or whatever it's called? And or do you think it's cheaper to get a 3D printer? It's probably cheaper to get a 3D printer, right? You're looking at $30,000 versus several $100s. And on top of that, however, in order to machine metal, you have to take the metal away from the part. You start with a big old hunk of bar stock, and then at the end, you probably wasted half your metal because you machined it into a part. Everything else is, we got metal shavings all over the floor. Number one, you got to pick those up. People step on them and splinters in their foot, but I don't know. Anyways, the deal is, the companies need to buy the metal for the finished product and the metal that will be milled away. You can't just get one or the other. You have to get the entire stock. You don't sell it anywhere else. The 3D printer, however, uses as much material as you need. If you want 200 cubic millimeters, you use 200 cubic millimeters. It adds it as it goes up, right? So, what if you could 3D print metal? Wouldn't that solve the problem? Well, unfortunately, that's just as expensive as getting a lathe or a mill. A metal 3D printer is really hard to make because you would have to make your nozzle, your extruder. You have a much higher temperature, melting point or whatever, than the metal that you're printing. And it's very expensive too. It's very hard to make. Imagine how much electricity and energy that takes to melt down metal at a constant fluid rate. A lot, right? In fact, this isn't even something we mastered as well as plastic 3D printing. So, as I said, it's expensive. It'll inflate the cost of an eBay auction. Anybody who's done on eBay, you buy something they really want. The week that the auction is in place doesn't go up, but right in the last 15 minutes, whoosh! Subtractive manufacturing subtracts feasibility, additive manufacturing, which is 3D printing, adds feasibility. Because you only use as much material as you need down here. But up here, you have to get the waste material and material that you need. It's getting too expensive. And 3D printing is increasing at an exponential rate as per Moore's law, which is slowing down. That's another topic for another time. Well, you might be asking, Alan, really? You haven't given us any evidence whatsoever. Well, my internship is involved in proving this. That's the whole thing. That's the crux of the whole thing. The scientific method says that you need irrefutable evidence something works before you can say it works. And it works with that, you're using a finite element analysis program called COMSOL. That's what I'm currently studying. And I'm going to be using COMSOL to simulate the heat transfer. And in designing heat exchangers, either me or another intern, we don't know yet, we're going to be using SolidWorks. And that's going to be, they're considered industry standard in both these programs. They work very well. And there's lots of rules online, and I should be able to work this program very nice. And that'll be my job. As I've said, internship hasn't gotten off just yet. My professor is very busy, and things haven't been going very quickly. So I kind of had to leave this one. This isn't the end of my internship like it is for all of you. Mine's got mine goes on. So yeah, so my conclusion is 3 parts. Number 1 is what did I already know coming in. Number 2 is what did I want to learn. And 3 is what did I actually learn. Well, what did I already know? Well, I wanted to test the waters of engineering. I wanted to make sure it was the right field for me because I didn't know what an engineering job would be like. Is it like The Office? Is it like working at Microsoft, where if you're a software engineer, you can just walk in wearing cargo shorts and a t-shirt? Like really, what is it like? Well, every company's different, right? So if every company's different and you want to know how it's different, you got to take initiative. You have to ask your boss what the policy is. You have to make sure you're doing it right. Any professor who knows me knows that I come into their office and I ask, am I doing it right? Am I doing it right? I might annoy them, but it's essential. On top of that, I knew basic heat transfer mathematics, so I knew I would have a good time. I knew I would learn a lot regardless. Conclusion 2, what I want to know. Well, I wanted to learn how to properly do my part in a real world engineering project. Because the deal is, to make something like Windows, or to even make something like an Airbus airplane, or a Boeing, it doesn't take one engineer, it's hundreds, maybe thousands of engineers. They all have to work together, and that is a daunting task to work together and make something that big. This is a smaller scale project. It only has maybe 6 or 7 engineers. So it's a lot easier. It kind of helps me learn the ropes of the whole thing. I also wanted to learn how to use COMSOL and also SOLIDWORKS and put it in the additional skills section of the resume. And I'm autistic. I don't have very good social skills. I'm not using that as an excuse or a crutch. I do not have business skills. That's my weakness. So I wanted to better my interpersonal skills, because social skills are essential to a job, like doors and windows are essential to a house. I also wanted to have job experience in the field of engineering. While engineers may be in very high demand, you still need job experience to get a job. Remember, the great workforce paradox. What did I actually learn? I learned quite a bit. My boss was nice enough to tell me the secrets of being a star employee. Here's some of what he said. Number one, take initiative. If you don't know something, ask for it. Because if you don't ask, you don't get. Dr. Meany up there, his door says, don't ask, you don't get. And I wholeheartedly agree with that. Take initiative, then you do what you're told. Well, doing what you're told is probably one of the most important parts too. Because if you don't do what you're told, how is anything supposed to get done? You know, my boss would ask me to design something in COMSOL, and what, I design pipe organ pipes or something? Well, how would he value me as an employee if I can't do what I'm told? But he can't, right? So I'd be out of there, right? Well, doing the extra mile is always going to help you in life. I don't care if you're working as a job, I don't care if you're working out of your job, I don't care if you're with a family, it doesn't matter. Every area, including jobs, doing the extra mile is always nice. And this may be the last one, but it's probably the most important. It falls under take initiative, but I put it in here just how, this is just to show you how important it is. Communication, communication, communication. You have to communicate with your coworkers, you have to communicate with your boss, and then you got to communicate with the customer. It's all about communication, because none of you, no one is a mind reader. You cannot assume somebody's thinking a certain way and just act out. Because then you walk into the person and say, I thought you did that. For example, what if I were to walk into a house? Like if I were to I would lose my house key. My brother were to say, Alan, you have the key, and I thought you had it. You can't do that on the job. Nothing will get done. You gotta have communication, you gotta have all these. If you can do these four things, your boss will love you. And so will your professors. And what about the math involved? Well, heat transfer is considered one of the hardest classes Poly offers in the mechanical engineering program. I'm looking forward to it, and that's another reason why I took this internship, just to prepare myself for heat transfer. And here are the two equations that I will be working with most. The heat equation and Fourier's law. I don't want to get into too much of this because it may have gone over time. Although, this is just change the temperature relative to time, change the temperature relative to x, thermal conductivity. You separate the variables, you solve for your eigenvalues, and you're good to go. But this is just an ordinary differential equation of what can be a partial or it works. But those are the two most important equations. But you learn to form this equation in chemistry for every freshman year. Instead of derivative of time with respect to x, it's just delta t, because you haven't learned differential equations yet in that course. Once you pass that, you move to calculus. What was that? Well, to conclude, I want to say that I had a great time with my internship, and I had a great time talking to all of you. I think that I hope I've communicated well, and I hope you have learned a lot from this internship and this presentation as I have. I hope you all have a great day.